Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you very much for giving me this opportunity to present my work. So good evening everyone. I'm going to talk about functional site prediction by exploiting correlation between labels of interacting residues. Sounds like Greek and Roman to most of the people over here. But as far as machine learning community is concerned, this problem is about handling extreme class imbalance in the network data setting. So that will be clear. So to begin with, what I'll do is I'll motivate the problem from the point of view of protein structures. So what you see on your left is a protein structure which is made up of amino acid residues. It's a three-dimensional structure. It's a collection of 3D coordinates. So this particular protein has 212 amino acids, out of which 4 amino acids which are marked in the structure are important for its function. So these amino acids will be called as functional residues. And rest of the amino acids are not important for the function, hence we call them as non-functional residues. So one can represent functional and non-functional residues in form of a vector, which is f on your right. It will be a binary vector with entries 1 wherever the residue is a functional residue. So in this particular case, I have a vector of 212 length with 4 entries being +1 and rest of the entries being -1, meaning it's not functional. So you can see the extreme class imbalance in this particular setting. So we represent this particular protein structure as a graph, as undirected and weighted residue interaction network, where nodes are amino acids and we connect two amino acids if they are in contact with each other. Then there is a label vector y on, so there is a label that we are interested in assigning to each of the amino acid. And there will be another term that we'll be using. I'll introduce that term right now. It's called as polarity of interaction between connected residues. So now if two amino acid residues or two nodes are connected, I look at their label and assign a weight to the edge based on whether they agree in terms of their label or not. So wij will be +1 if y and yj which are connected, so if residue I and j are connected also agree on the label, then it will be +1. It will be -1 if they don't agree on their label. So the edge labels will be +1 and -1. We call them as polarity of interaction. And the node label will also be +1 and -1. Is the setting clear? So why is this interesting for ML community? So there is an extreme class imbalance. On an average, 0.07% amino acids are functional and rest of the others are non-functional. So extreme imbalance here. And it's a network data setting, and due to imbalance, it's hard to apply existing collective inference techniques. So we formulate this particular problem. So this is the formulation of our problem, where we are interested in getting label vector y such that it minimizes the node-wise label misclassification, which is the first term, and it satisfies maximum number of polarity constraints, or in other words, it violates minimum number of polarity constraints. That's the second term. So yi tilde is the one that is the label predicted by our method, and yi is the actual label, and wij is obtained by obtained using predicted labels, and wij is the true polarity of interaction. So there are two terms. One is node-wise label misclassification, and second is polarity constraint violation. And so the existing methods in the literature, what they do is they only concentrate on the first term. They ignore the second term. wij tilde is polarity of interaction computed from the predicted labels. The predicted labels. Right, so they should also agree. So wij tilde and wij should also agree. And note that minimizing just the second term is not sufficient, because it may lead to configuration with wrong labels. It's easy to see that particularly. So this is the problem that we want to solve, and we solve this particular problem in 2 steps. And this is the overview of our approach. So we take 3-dimensional protein structure as input. We make RIN or construct residue interaction network, and then we apply local classifier in order to take care of the first term, that is node-wise label misclassification. And we also learn what is called as interaction polarity classifier. I'll tell you why interaction polarity classifier is required. So look at the second term, which is polarity constraint violation, where Wij is computed, if you remember it clearly, Wij is computed from Yi and Yj's, right? And the true Yi, Yj's are not available to us because they are not, because I don't know the labels to begin with. So I need to use something to substitute for Wij. So since it is not available, we will predict it based on the attributes of the nodes. So that will be covered in the interaction polarity classifier, and then we take input of both these classifiers and feed it into iterative collective inferencing scheme. I'll explain that in the next slides. And finally, the iterative collective inferencing scheme gives us list of functional residues. So first I'll explain learning of interaction polarity classifier, where we are interested in predicting the age label for the protein residue network. So what we do is we first concatenate features of the residues and make a concatenated feature vector xij, and then train a logistic regression classifier with L1 regularization, which will give us the probability of Wij being 1 given the label vector. And in the same manner, we use again logistic regression classifier with L1 regularization for predicting the node label, and use this in the setting of iterative collective inferencing, which is the main piece of the work. So what happens is this iterative collective inferencing scheme, it's an iterative procedure which first obtains the polarity from the polarity classifier, which is W hat, and also gets the label from the local classifier, that is Y hat, and initialize Y tilde to Y hat, which is the label obtained from the local classifier. And now the idea is to adjust the label on nodes such that we satisfy most of the polarity constraints, right? And now these polarity constraints are given in W hat. These are predicted polarity constraints, since the actual polarity constraints are not available to us. So what we do is, so for at each node, we obtain the vote from its neighbor and find out how many of my neighbors are positive. How many of my neighbors are positive, and based on that, we have a cautious update that we make here. So this is the step where we obtain a number of positive votes from the neighbors, and then we update the label based on some kind of a cautious mechanism. So I will retain the label as +1 if my Qi or the number of votes are greater than 0.5 and lambda. So lambda and beta are some tunable parameters, and they essentially control the label update. And this cautious approach helps us in minimizing node-wise label misclassification cost while satisfying most of the polarity constraints. And we applied this method on CATRES-FAM benchmark dataset having 140 proteins, where 471 out of 49,000 residues were functional. And we use precision recall as measure for evaluating performance. And what we saw is the collective inferencing scheme, that is our scheme, improves precision by approximately 5 percentage point and recall by 29 percentage point. Discern, which was relational classifier, and CRF, so our method outperforms both of those techniques. And the local classifier that we use to predict node label has precision of 14.38 at recall of 69 and recall of 58 at precision of 18%. So this is the accuracy of the local classifier that we use for predicting node label. And after applying collective inferencing scheme, we can jack it up to 23% and 87% respectively. And if you use the actual interaction polarity constraints as against the predicted one, the precision can be jacked up to 80% and recall to 94.35%. But current challenge is in getting right kind of features in order to accurately predict polarity of interaction constraints. So we exploited interaction residue label correlation, and we achieve significantly better performance. And this technique can be applied in other network data setting. So I forgot to mention this is joint work with my colleague Professor Ravindran. He is in the audience, and a couple of my students at IIT Madras. This work will appear in ACM BCP conference, upcoming ACM BCP conference. Thank you.